Assalamu alaikum class. I hope that all of you are well and safe in your homes, inshallah. This is the lecture 19 and 20 of our course Signals and Systems and covers Laplace transformation from chapter 9 of our textbook. Today we will be discussing Laplace transform, properties of the region of convergence associated with the Laplace transform, and how to determine the inverse Laplace transform. Well, in one of our previous lectures, in fact I think it was the last lecture, I introduced the concept of an operator, and we discussed two operators. One was the derivative operator and the other was the system operator. So Laplace transform in a similar way can be thought of as a transform operator, which takes an input signal in time domain and produces an output signal in another domain. Laplace transform you have already discussed in one of your earlier mathematical courses, but we are going to study Laplace transform again, because when you do it in mathematics, you do it from a mathematical point of view, but when we are doing it for our course Signals and Systems, we'll be applying Laplace transformation to signals and systems, which although are functions, but we'll think of them as a signal or a system. Laplace transformation is defined as Laplace transform of f of t, which is f of s, and what you do is you define the function f of t by a complex exponential e minus st, and you integrate it into the interval from minus infinity to plus infinity. So what is happening? This operator L is transforming a function of time domain into a function of s domain. Laplace transformation is a two-directional process, or is a bidirectional technique, which means that if a function ft has a transform f of s, if you take f of s and you take inverse Laplace transform, you can get f of t. Now the variable s is a complex variable, and we have already discussed this variable when we were doing the stability with respect to complementary solution. This variable s is the same variable. It can be represented as a real part sigma and an imaginary part j omega. So we see that Laplace transformation is converting our function in one domain from a function in the other domain. But what advantage does this offer us? This offers us a number of advantages. For example, we'll see that after transformation, certain functions are very easy to apply. For example, convolution in time will simply become multiplication when we take transformation, or solving differential equations will be easier if we apply Laplace transformation. It must be kept in mind that Laplace transformation is a function of continuous time variable and will be applied to continuous time signals and systems only. The second and major advantage of Laplace transform is that it can be applied to the analysis of many unstable systems. We'll see that there are some transformation techniques which are very useful, but one cannot use them for analyzing unstable system. The advantage of Laplace transformation is that we can investigate the stability and instability of systems through this technique. So how does the S-plane look like? Since S-plane is a complex plane, therefore it has a real axis and an imaginary axis. The real axis is the sigma axis and the imaginary axis is the j omega axis. So all complex planes are divided into 4 quadrants. Similarly, the same is going to happen for the S-plane, where the first quadrant is the case where both sigma and omega are positive. The second plane is the case when sigma, or the real part of the S-plane of omega part is positive. The third quadrant is where both sigma and omega are negative, and the fourth quadrant is the case where sigma is positive but omega is negative. Let's determine the Laplace transform of a unit step function. As we have just discussed in this course, functions are basically input signals. So this this unit step function is going to be the input to a system. To determine the Laplace transform, we have to integrate the function from minus infinity to infinity. But since our unit step function exists during the interval 0 to infinity, we integrate it during this interval, and after integration, this is what we get. Now, if you look at the result carefully, you will see that e raised to the power minus st is representing a decaying exponential or a rising exponential depending upon what is the value of s. So when does this e raised to the power minus st represent a decaying exponential? Right, it is when the value of s is positive, so the exponential has a negative power. When the exponential has a positive power, which means that when s is negative, this is a rising exponential, and as t will approach infinity, this will become infinity. So we can say that the Laplace transform of the unit step exists only if the real part of s is greater than 0. Why the real part? Because we remembered that the imaginary part has nothing to do with the decay or rise of the exponential. It just was the oscillation frequency. So we can denote the situation by Laplace transform of unit step function is 1 by s, where real s is greater than 0, which means that s is negative. Which means that s is positive. Real part of s is positive. Therefore, the following transform pair exists. Unit step has a transform of 1 by s. This brings us to the definition of region of convergence. From the previous example, when we determined the Laplace transform of a unit step function, we saw that the Laplace transform was 1 by s only if the real part of s was greater than 0. So we saw that the Laplace transform exists only under a certain condition, and it does not exist if the condition is not true. So this means that whether the Laplace transformation of a function exists or not depends upon the complex variable s as well as the signal. For example, in which interval is the signal defined. And all complex values of s for which the integral converges are known to form a region of convergence, or ROC, in the S-plane. Laplace transform exists only if the argument of s is inside the ROC, and the imaginary part, j omega of the complex variable, has no effect in terms of convergence. So the ROC is determined solely by the real part, sigma. The region of convergence is a very important concept in Laplace transform. And given a Laplace transform and the region of convergence, we can determine what type of signal we are dealing with. As an example, let's see the signal e raised to power minus at u of t. As we can see that this signal is going to be a right-handed signal because the complex exponential is being multiplied by unit step function, and because of the presence of unit step function, the complex exponential will start from 0 and continue towards infinity. Substituting the value in conventional Laplace transform formula, we get minus 1 by s plus a, limit t approaches infinity, e minus s plus at minus 1. Now again, this is an exponential function, and as we remember from the previous slide, an exponential function, the trend follows is if the power of the exponential function, negative exponential function, is positive, it means that the exponential is indeed a decaying exponential, and as t approaches infinity, the value of the function approaches 0. However, if the power b is negative, which means that the overall power of the exponential is positive, then it's a rising exponential, and the value of exponential function increases infinity as time approaches infinity. So we can say that this Laplace transform will exist only if the real s plus a is positive. This is positive, so that the power is negative, power of the exponential is negative, or real s plus a is greater than 0. So the Laplace transform of e minus at ut is 1 by s plus a, given real part of s plus a is greater than 0, and this real part of s plus a is greater than 0 forms the region of convergence. In case we say that a is real, this means that a real part of s is greater than minus a. We just take this a on the right hand side of the equation. If a is complex, that is, the power of the complex exponential we were dealing with is a complex power, then the condition is real of s is greater than real of a minus real of a, and again we see that the complex part of the power has no part to play in the region of convergence. Let's try to solve another example. This time our signal is e to the power minus at multiplied by u of minus t. Now since this exponential is being multiplied by this unit step function, let's look at the unit step function first. Now u of minus t is a unit step function which is flipped along the time axis, which means that now it is existing from the time t is equal to minus infinity to t is equal to 0, or along the negative time axis. When an exponential is being multiplied by a function, a unit step function like this, which is on the negative time axis, this means that our exponential will also exist from the interval t is equal to minus infinity to t is equal to 0. Or in other words, this is a left-hand sided signal, where left-hand side means that it is on the left-hand side of the time axis. So once we determine the Laplace transform, we get a function like this, where our time limit starts from t is equal to minus infinity. If we look at this trend for a function e minus bt, u of minus t, we'll see that once the power of exponential is positive, which means that our exponential is a decaying exponential. It means that when time is equal to minus infinity, the value e minus bt is infinity. And when this b is less than 0, which means that the power is negative, it means that e has a positive power. Our exponential will start from 0 at time minus infinity, and will have a some power value at t is equal to 0. Now why do we observe this trend? Is because of the presence of u of minus t. Our time scale is negative, so in the power both b, the value of b, and the value of t should be taken into consideration. T is negative now, which means that this actually becomes e raised to the power plus b of t if we are looking at it in a conventional way. So the Laplace transform only exists if real power of the exponential is negative, or real s plus a is less than 0. If a is real, means real s is less than minus a, again you can see that this a is being taken on the right side of the inequality. And if a is complex, when the ROC's real S is less than real of minus A. Now let us summarize the significance of region of convergence. We solved two examples. In the first example, our signal was e to the power minus at into u of t, which was a right-hand-sided signal. What right-hand-sided signal means that it existed along the positive time, or from time t is equal to 0 to time t is equal to infinity. And we saw that the Laplace transform of the signal was 1 by s plus a. Similarly, when we see a negative time signal or a left-hand-sided signal, which is minus e to the power minus at u of minus t, and why is it a left-hand-sided signal? Is because it existed from time t is equal to minus infinity to time t is equal to 0. We see that it has the same Laplace transform, which is 1 by s plus a. Now, both these signals, which are different signals, are giving us the same transform values. How do we know which signal is from the ROC? In the first case, we see that the ROC is such that the Laplace transform exists in the region when real of S is greater than minus real of A. What is minus real of A? Basically, minus real of A means, or minus A means that it is greater than the value minus A. Now, if we try to plot the value minus A in the S-plane, since it is a real value, it means that our real value is fixed to minus A, where the imaginary values can take any value. So it is going to be a straight line. And greater than, ROC greater than real of minus A means that the ROC is all that portion which lies beyond that minus A value. So the ROC is greater than real of minus A, or the ROC is this plane. For the other signal, we see that the ROC exists from real S is less than minus real of A, which means again that we draw a line for real values of minus A, which is a straight line, because along the straight line we'll always have minus A in the real value, and the value of omega could be anything, or the imaginary value could be anything. And now our Laplace transform exists when when our values, or our ROC is in the values which are less than this value, real of minus real of A. So this is this plane, that is the range, or this ROC extends from minus infinity to minus A in the S-plane. We see that in both cases we are just considering greater than or less than, which means that our ROC will be just beyond or just behind this minus A point. So if we are just given the Laplace transform and the ROC, when the ROC is greater than some value, we will know that it's a right-hand-sided signal. And when the ROC is less than some value, we'll know that it's a left-hand-sided signal. Now, we see that same Laplace transform may correspond to different time domain functions depending upon the ROC. So class, so far we have seen that how can we determine the Laplace transform of a signal, and the Laplace transform of a signal is defined in a certain area which is known as the region of convergence. We have seen that the Laplace transform individually or independently is not unique. 2 or 3 functions might have the same Laplace transform values. However, it is the region of convergence which makes it unique for each of those signals, 2 signals or 3 signals that might have the same Laplace transform. The existence of a separate region of convergence is what makes the overall Laplace transform unique for each of those signals. We have seen that based on the ROC, we can see or say whether a function is a right-hand sided signal, that is whether it exists in the positive time only, or a left-hand side signal, that is whether it exists in the negative time only. Now let us determine the Laplace transform of one of very common signal used in engineering, which is an impulse function or a shifted impulse function. When we determine the Laplace transform of a shifted impulse, we can apply the shifting property, and the shifting property says that whenever an impulse is being multiplied by a function, we have the value of the function at the instance of the impulse. Since this impulse was existing at time t is equal to capital T, so we get e raised to power minus s capital T, where capital T was the instant at which the impulse was existing. As the Laplace transform for this impulse was determined based on capital T on the existence of impulse only, so what is the ROC, or region of convergence, of this Laplace transform? Well, it is the entire S-plane, because the integration is independent of the value of S in this case. So the Laplace transform of an impulse is, shifted impulse is e raised to power minus st with ROC entire S-plane. Similarly, for an impulse occurring at time t is equal to 0, what is the Laplace transform? We'll just substitute t is equal to 0 over here and we get 1. And ROC is again the entire S-plane. Now let us extend the concept of Laplace transform to a sum of signals. We'll see that Laplace transform obeys the laws of linearity, which means that the Laplace transform of a sum of signals is the same as the sum of Laplace transform of these individual signals. So we'll take two signals, both of which are right-hand sided exponentials. The first exponential is 3 e raised to power minus 2t, and the second one is e raised to power minus 2t. Once we determine the Laplace transform, we can see that it is s is 3 by s plus 2 minus 2 by s plus 1. Now, what about the region of convergence for this sum? We know that for the function e raised to power minus t ut, since it's a right-hand sided signal, the ROC is greater than, is real of s is greater than minus 1. And for the signal e raised to power minus t 2t, the ROC is real of s is greater than minus 2. Just pause over a second and observe the similarity. We can see that whatever the root or the denominator, the root of this denominator is, the ROC is always greater than that value. We'll extend this concept in the next slide, but so far we can say that for the first case, the ROC is real of s is greater than minus 1, and for the other one, ROC is greater than minus 2. How would these ROCs look like? If this is our S-plane, ROC greater than minus 1 would be, this is our minus 1 point, so this will be this region, all this region. So this is our ROC, and for the ROC, our real s is greater than minus 2, if this is our minus 2 point. So the ROC is all this region. So in summary, the ROC for a sum of exponentials is the combined ROC. For both of these regions, we can see that the region real s is greater than minus 1 was the common region. So we can say that the ROC is our real of s. At the end, real of s is greater than minus 1. This has been solved and a composite form has been obtained. For a rational function, the concept of poles and zeros is used very frequently in signals and systems. Now, a rational function is generally a ratio of polynomials of the form qs by ps, where qs is the numerator and ps is the denominator. If the numerator and the denominator have no terms in common, then our rational function is in the reduced form. For a rational function, the roots of the denominator ps are known as poles of the system. These are the values where the function is undefined, because if the denominator is 0 or is being multiplied by a factor 0, which means the entire denominator is 0, then our function becomes infinite. So a pole means something which is very high. So a pole at a pole, the value of a function will be infinite, will be very high, which can be seen from this figure, where we have plotted a very simple function 1 by s of the form 1 by s, 1 by magnitude of s in fact. And if we plot this function, we'll see that this function has one pole, and the value of pole or the root of the denominator is at s is equal to 0. So at s is equal to 0, the value of this function goes infinite. Hyperlinked with this picture is a link from OpenCourseWare at MIT. You can see this link and understand the behavior of a pole if you want to explore it even more. In the S-plane, a pole is generally depicted by an X. Similarly to poles, if we solve the numerator of this rational function, or the root of the numerator is known as a 0. And this is the value where our rational function becomes 0, or the value of the rational function is 0. Therefore, it is known as a 0 of a system. It is depicted by an O in the S-plane. Now let's look at the Laplace transform of previous example. We can see that the root of the numerator was at s is equal to 1. So we have a 0 at s is equal to 1, and we have two poles at s is equal to minus 1 and minus 2. And from the previous example, we can see that the value of ROC was greater than minus 1. So this brings us to the conclusion that the ROC does not contain any poles. So far in all the examples, we have seen that the ROC did not contain any poles, and this is a standard rule that for a Laplace transform, the ROC does not contain any poles. Now let us determine the Laplace transform for the function xt is e raised to power minus b of t. We can see that this signal is not being multiplied by any unit step function, which means that it exists from time minus infinity to time t is equal to infinity. So it's neither a left-hand sided signal nor a right-hand sided signal, rather it's a two-sided signal because it exists on both sides of the time axis. If we plot this signal, we see that it can be plotted for both values of t, since we have been given no restriction on the value of b. So b can either be positive, greater than 0, or b can be negative, less than 0. If we plot it that way, we can see that for the values of b greater than 0, the power of this exponent is negative, which means that it will be a decaying exponential. If the value of b is less than 0, it means that the overall power of this exponential will become positive and it will be a rising exponential. Now Laplace transform exists for only one of these signals, and we can guess which one, but we'll see and then we'll conclude a result at the end as well. So if we determine the mathematically Laplace transform we can determine it by dividing the signal into two parts. The first part covers the positive range or the right hand sided range, and the second part covers the left hand sided range. So for the right hand sided range, we can say that it is equal to e raised to power minus pt u of t, whereas for the left hand sided range, that is when time t is negative, this negative power of b multiplied by the negative power of t becomes a positive power, and this is what we get. So when we determine the Laplace transform of each part individually, for e raised to power bt u of minus t, using our examples, what we have derived in the previous examples, we can say that the Laplace transform is 1 by s minus b, and since it's a left hand sided signal, so the region of convergence is less than the pole, re of s is less than b. Similarly, for this right hand sided signal, the Laplace transform is 1 by s plus b, again applying the formulae or the properties or the examples we've done so far. And since it's a right hand sided signal, so the real part or the ROC is greater than minus b. Let's say that we intend to plot this ROC. So this is our S plane, and say our b is equal to, since b is greater than 0, so b is equal to 4. So for the left hand sided signal, when ROC is less than b, our ROC is less than this portion. Similarly, for the right hand sided signal, our ROC is greater than minus b. Since b was 4, so that means we'll draw a line at minus 4, and our ROC is greater than origin, so this is our ROC. Now our concept of linearity has told us that the resultant ROC is the intersection of both these ROCs. So the resultant ROC for the example drawn, for the figure drawn, is between minus 4 to 4, or for the overall case, the ROC is between minus b to b. What happens if we look at the second case, which is when the value of b is less than 0? In that case, let's assume that our value of b is minus 4. So drawing our S plane, for the right hand sided part, right hand sided signal, when real of s is greater than minus b, so minus 4 becomes plus 4, so our ROC is this region for the right hand sided signal. For the left hand sided signal, let me change the marker color. And I'm unable to change the marker color, so let's say I'm using the green color again. So for the left hand sided signal, our ROC is real of s is less than b, which means that real of s is less than minus 4. So this is minus 4, and this is our ROC. So now the ROCs do not intersect, and we can say that for the case when b was less than 0, we have no Laplace transform. And that is what we can say intuitively as well, because we see that for the case when our function b was less than 0, it was an increasing or rising function, and therefore its Laplace transform should have existed. So which means that we can say that our result looks something like this, as shown in the figure. And what happens when b is less than 0? Obviously there is no intersection of ROC, hence no ROC, and correspondingly no Laplace transform. So far we have seen Laplace transform, and through different examples we saw that Laplace transform for a function is completely defined by an expression along with the ROC. There are certain properties of this ROC which can be listed henceforth. For a finite duration sequence that is absolutely integrable, ROC contains the entire S-plane. For example, as we saw in the impulse function, the impulse is a finite duration signal, or it is a signal which has only a fixed number of points. And we saw that the Laplace transform, since the function was not the Laplace transform was not a rational function, therefore it had no denominator, and it was not depending on S, and the ROC was the entire S plane. What does the condition that is absolutely integrable mean? It means that the function, in whatever range it is defined, should not become infinite at any point. You might argue that the impulse gets infinite, but we have always introduced the impulse through the direct delta function, and we have said that it's a unit magnitude impulse. That means that the area under the impulse becomes 1 and it's absolutely integrable. For signals whose Laplace transform is a rational function, ROCs do not contain any poles, and it's a vertical strip or plane bounded by poles. This we have seen in all the examples, that whenever the Laplace transform was in the form of a rational function, the ROC was always either outside the poles or inside the poles or within two poles. So that means it is either a vertical strip in case of it being between two poles, or a plane, which means that it will be a region which will be from a certain pole to plus infinity or minus infinity. Why is it a vertical strip? Is because we remember that for determining the ROC, we always look at the real part of the S-plane. And the real part of the S-plane is a vertical strip because it has one value, and the value of an imaginary part could be anything. So that means it gives us a vertical line. In case the Laplace, third property is in case the Laplace transform is rational for right-hand sequences, the ROC is the right of a pole, and in case it has multiple poles, it has the right of the rightmost pole. For example, in example 2, we had a right-hand sided sequence which had only one pole, and we saw that the ROC is towards the right of the pole. And in example 5, we saw a sum of two right-handed sided sequences, and we saw that the ROC was outside the outermost pole. We had two poles at S minus 1 and minus 2, and the rightmost pole or the outermost pole was S is equal to minus 1. So the ROC was greater than S is equal to minus 1. Similarly, if the Laplace transform is rational for left-hand sided signals, ROC is the left of the leftmost pole, and we saw it in example 3 where we had a function which was being multiplied by u of minus m, and we saw that the Laplace transform, the ROC of the Laplace transform was less than the pole value, or towards the left of the pole. Similarly, if we had a sum of exponentials, the sum of left-handed sided sequences, the Laplace transform would have been on the left of the leftmost pole. For double-sided sequences, ROC is a central strip or does not exist, as we saw in example 6 we just did, that if the ROC does not overlap, then it does not the Laplace transform does not exist. And finally, for a linear sum of signals, the ROC is a single connected region which is the intersection of all ROCs and does not contain any poles. Again, as in example 5, the ROC is always going to be a connected region. It's not a disjoint region. For example, you say that we have 3 poles and the ROC is between one region and two region. The ROC is always going to be a connected region. It is not disjointed. Given on this slide is a table for Laplace transform of some elementary functions along with the ROC. This table is going to be very useful to determine the Laplace transform as well as the inverse Laplace transform, which is to follow on the next slide. When the concept of Laplace transform was introduced, it was introduced as a two-sided transformation, which means that if a signal or a function f of t is transformed into f of s using Laplace transformation, then using inverse Laplace transformation, the same f of s can be converted into f of t given the ROC. So by definition, the inverse Laplace transform is defined as x of t is x of s multiplied by a positive exponential this time and integrated between the limits sigma minus j omega to sigma plus j omega, where this omega is approaches minus infinity, varies from minus infinity to plus infinity. So we'll be integrating along all these vertical lines or contours along the S-plane for which the ROC was possible. Now, evaluating this integral requires the knowledge of contour integration, which is beyond the scope of our course. So we'll be resorting to a much simpler method. The method we are going to use is the method of partial fraction expansion. We are given a rational Laplace transform in the ROC. We can determine the time domain function. And how are we going to determine the time domain function is that first of all, we'll divide the algebraic expression into a linear combination of lower order terms, and by inspection, we'll determine the transform of each of these terms. So these steps for determining the inverse Laplace transform for a rational function x of s would be: number 1, factorizing the denominator; number 2, taking the partial fraction expansion of the function x of s so that we can express the function as a linear sum; number 3, for each term in the linear sum, determining the inverse Laplace transform through inspection if we have conditions given or through a table. So let's say we determine the inverse Laplace transform for x of s is equal to s plus 3 by s squared minus s minus 2. First step, factorizing denominator. Once we factorize the denominator, we see that we can express it as the product of two factors. Second step, we'll determine the partial fraction expansion. So this partial fraction expansion gives us a value for a and b. Before factorizing this denominator, we observe that this function x of s has two poles and one zero. The first pole is at s is equal to minus 1. The second pole is at s is equal to minus 2. And the zero of the expression x of s is at s is equal to minus 3. Now we know that the ROC is determined from the poles and the zero has no part to play in it. But wait, do we have an ROC mentioned? No, we do not have an ROC mentioned. So what is the strategy? Well, we'll plot the Laplace the x of s or the S-plane, and we'll see that what possible ROCs we have. So we can say that each of these terms belongs to a left-hand sided function, and so our ROC is to the left of the leftmost pole, which is minus 1. Or as a case 2, we can say that one of the functions is a left-hand sided function and the other function is a right-hand sided function, and our ROC is a disk or a strip between two poles, bound by the two poles. The third option is both of these functions are right-sided functions, and so are ROCs to the right of the rightmost pole. In case we say that our ROC is a disk, one of the poles, this one, would be a right-sided pole, would belong to a right-sided function, because for a right-side function, the ROC is towards the right of the pole, and this will belong to a left-side function, so that its ROC is inside the pole. But in any case, we see that our ROC is a connective region. So for the first case, when we say that both of these fractions belong to left-hand sided signals or left-sided signals, we will use the identity or the formula that when a signal is left-sided signal, the denominator of the ratios of the form 1 by s plus a. So applying the inverse transformation, we'll get e to the power minus t u of minus t for the first expression, which is 1 by s plus 1, and e to the power minus 2t, e to the power 2t u of minus t for the second expression by comparison. And therefore we can say that this is our overall function. But we'll see that this function will diverge as t approaches minus infinity. Case 2, when we say that x of t is a two-sided signal. As we discussed, that it would imply that one pole, which is this pole, belongs to a right-sided signal, and this pole belongs to a left-sided signal. We have the formulae to determine the expressions, and we'll get this expression. Whereas, as we discussed, this pole belongs, or the minus 1 pole belongs to a right-sided signal, and the pole at 2 belong to a left-sided signal. We'll see that this function will approach a value of 0 as t approaches either plus infinity or minus infinity. The third case is for the situation where we say that the function x of t was a right-sided signal. So both this pole and this pole belonged to right-sided signals. Again, we have the formula for a right-sided signal, and after applying the formula to both these signals, we can get this expression. Now we'll see that as we substitute t is equal to plus infinity, this expression will diverge or will reach a value of infinity. So we saw after this example that determining on the ROC for the case of two poles, we can have three functions, and of all these three functions, only one function was such that its value converged. So if that function is used as an input, we can assume that signal is used as an input, we can say that its value will always be bound. However, if the first or third signal is used as an input, the value will not be bound, so it will not be a bounded input. But in any case, we have three different expressions for x of t. Summarizing today's lecture, we saw that Laplace transform is an operator that takes a time domain function and transforms it into an S domain function. So basically it is a transformation operator. Then it is a bidirectional transformation, which means that if a signal x of t has a transform x of s, so if we take the transform function x of s and take its inverse Laplace transform, we get the same time domain function x of t. And third, each Laplace transform is characterized by its ROC. So given the ROC, we can determine the time domain function if we want to determine the inverse Laplace transform. We saw that the ROC had a certain set of properties, and based on those properties, we can say whether a function is right-sided, left-sided, or both-sided. This concludes your introduction of Laplace transform. From next lecture, we'll look at some properties of Laplace transform. Thank you.